Who here has used Cassandra in a production application? Great. Okay, let's try and get that number up a little bit. So, my name is Matt. I work for Rap Genius in Brooklyn, New York. My connection to Cassandra is actually that at my previous project, we used Cassandra as our main data store. Basically, for every time a user signed up, we needed to consume a ton of data from a bunch of external APIs and store it and process it as quickly as we possibly could. And during that time, I fell in love with Cassandra. It was super solid, reliable, a pleasure to use. And I've continued to actually maintain the library I wrote for Ruby and Cassandra since leaving that project, and I'll tell you a little bit more about that. So, now that you know a little bit about me, why would you want to use Cassandra? I need to justify myself here. So, Cassandra gives you something that you probably aren't going to be able to get with the data stores that are most familiar to you. So Cassandra runs on a bunch of machines. You have a cluster. You stand up however many machines you want or can afford or need once you get good at figuring that out. And the data is distributed among those different machines. And every piece of data lives on generally, 3 machines is a common default. But no one machine holds all the data. So there's no master. There are simply a bunch of sort of equal nodes hanging out, talking to each other, and storing some subset of your data on each node. Now, something that's unfamiliar to those of us who might have worked with a more traditional replication environment in MySQL or Postgres is that the masterless nature of Cassandra means you can talk to any node you want when you're asking for data or writing data. So these machines are talking to each other, and if you say, I need this, these rows, and that machine doesn't have them, it knows who to ask for it, and it comes back to you. It's completely transparent. So you don't even need to be connected to every machine in the cluster, and you certainly don't need to pay attention to which machine you're talking to for any given request. So why is this good? First, if a node goes down, and hardware does go down, if a node goes down, you basically will not notice. So all of that node's data also lives on other machines, and the cluster will figure out, hey, looks like this node isn't here anymore, so I'll just go somewhere else for that particular piece of data. So you're really tolerant to failure, and that's something you don't have to worry about. Another thing you don't have to worry about is scaling. Well, you have to worry about scaling a bit, but if you have a single master data store and you have more and more data, you basically need bigger and bigger hardware. That's vertical scaling. Classic, we've all dealt with it. Cassandra means you can very effortlessly scale horizontally. So more data, just throw another node into the ring. And again, Cassandra is going to deal with redistributing the existing data among the new cluster or the expanded cluster without you really having to worry about that at all. Another really compelling reason to use Cassandra is that it's optimized for writes, high volume writes. And the main reason it's really good at that is because when you write data to Cassandra, it doesn't have to read existing data, modify it, and then write it back to disk. So the only thing it's ever going to do is either append to the end of a file or create a new file in response to a write request from you. That's just very efficient things to do in the world of computers. So that's fine, but actually the things I just described to you are true of a lot of options you have out there. So things like React and HBase and Voldemort. There's a whole class of distributed, masterless, write-optimized databases you can use. Why am I here talking to you about Cassandra instead of any of those others? So the problem with a lot of these big data stores is that the way they model data and the way you interact with them is pretty unfamiliar and can be pretty awkward. It can be difficult to map your domain model to the way these databases work. And for that sort of reason, Cassandra can be a better option. So first, the way Cassandra models data is in tables and rows and columns. So this should be really familiar. This could be a Postgres table. We have an ID, it's a primary key, that's a thing. and we have a couple of data columns. So you can dive right in and think about your data model similarly to how you think about it today if you're using a relational database. Even better, not only do we get a data structure that's like a relational database, we get a query language that's like a relational database. So Cassandra has CQL. CQL grammatically looks pretty much exactly like SQL. You can express yourself in many of the same ways. There are differences, we'll talk about them, but again, this is a familiar metaphor for interacting with data, and it allows you to really get going quickly. So I want to tell you about the downsides. I don't want to tell you about the downsides, but there are downsides. There are reasons you might not. There's a reason that like no hands went up when I asked who's using it. So full disclosure. First, the way you set up your tables, so when you define your tables, is going to constrain what you can do in terms of data access. So in a relational database, when you're setting up your schema, you really can kind of think about it in the abstract of, okay, well, I've got this data, it has a certain structure, how am I going to map it to tables and join tables and foreign keys and all of that sort of stuff. And aside from maybe creating some indexes and that sort of thing, we don't have to think too hard, at least at the beginning, about exactly what we're going to do with that data. That's not true in a Cassandra schema. So for instance, let's say we are making a blog. And I expect to be able to sort by possibly different columns for different use cases. That is just not, that's not an option. So Cassandra rows they have a single order. They always have that order. And the order by keyword actually only has one valid argument, which is that column by which the rows are ordered. So another reason we might not use Cassandra is we don't get any of those nice data integrity constraints that you get in a relational database. So a not null column, I want to say every row needs a value for this, not possible. Similarly, unique columns, just not possible. Foreign key constraints, I mean, there is no even concept of foreign keys or joins. So you can't lean as much on the database to ensure, you can't really lean on it at all to ensure that your data is in a valid state. Another fact about Cassandra is that CQL is a much smaller grammar than SQL. So that inner join there, the offset, neither of those things exist in CQL. It's not a relational database, so no joins. Offsets, subqueries, the list goes on. So it's a very, 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 essentially a small subset of what's possible in SQL with a couple of extensions as well. So, sorry. And finally, transactional support. So I'm going to send a statement. I'm going to begin a transaction. So I'm kind of in my own little world here. And I deleted my entire post table. Now, that's not going to be visible to anyone else yet. So I can just issue a rollback and go about my day like nothing happened. There are not transactions in this sense in Cassandra. So you can batch together several writes and send them as a single statement to Cassandra, and those are guaranteed to either all succeed or all fail. And they will be somewhat isolated in ways that probably aren't worth getting into. But these sort of transactions that span multiple statements, and you can do application logic in between while you're doing it and read stuff that you can see that other people can't see, that is not a thing. But distributed, masterless, failure tolerant, horizontally scalable, and optimized for writes. This is still a very cool piece of technology. So let's talk about how to do things right and do things in a way that will give you a very performant, very robust, always working perfectly kind of Cassandra data model. So we're going to make a blog. Here is some CQL to create a blogs table. It should look very familiar. Probably the only thing that might jump out at you is that our primary key is not an integer and it's not auto-incrementing. So we could make it an integer, but there's no auto-incrementing. You always specify explicitly when you create a row what the primary key is going to be. So you have a couple of options for how to make that work within your application. One of them is pick a natural key. So in this case, subdomain is going to be a natural key, so we're going to make that the primary key for our blog table. Other than that, though, this could basically be SQL. So here things get a little more interesting. Not that great to have a blog without posts. So there are two columns in our primary key here, and those two columns actually play very different roles. So this is a compound primary key. The blog subdomain is what we call a partition key. And what that's going to do is it's going to group together related data. And it's going to do that in a way that's meaningful, as we're going to see, all the way down to how it's actually stored on disk. So it makes a lot of sense in a blog to group together all of the blog posts for that blog. And then secondly, we're just going to have a plain old ID column, and we're going to make that a UUID. So usually unique ID is your other good option for dealing with a non-auto-incrementing world. And that's called the clustering column. And the clustering column actually defines the order of the rows within a given partition key. And they are always in that order. And a UUID is actually really useful for this if you want to order by some sort of timestamp, because a type 1 UUID actually encodes a time as well as some random or randomish data. So when you sort by a type 1 UUID, you're actually sorting by timestamp. You're sorting by creation time of that ID. So let's juice this up a little bit and add a secondary index. So that is something you have available to you in Cassandra, and it's great. Secondary indexes are not a cure for everything. They are not specifically not something you should sort of base your main access patterns on. But in this sort of situation, we have authors, and we at certain points would like to look up what has this author written, and we can absolutely do that. Now, you can have more than one secondary index in a table, but you cannot have more than one column in a single secondary index. And finally, let's add a collection column. So this is a very cool, fairly new feature in CQL. And we get sets, we get lists, and we get maps. And we actually get essentially atomic operations on those collections, much like you get in Redis or Mongo. So I can just say, add this element to this set at, in this row. And I don't have to read the existing contents of the set. I don't have to persist them back. And you get basically anything you would expect for these types of collections. There is an atomic write operation you can do on it. So that's very cool. So we're going to dive a little bit under the hood here, and it's going to motivate the way we've structured our data model so far. And we're going to get a little bit into the weeds. And the reason I want to talk to you about this level of things, because it's a level of things you never have to directly interact with, but that project where I used Cassandra and loved it, and it worked like a dream, and it was amazing, that was actually the second Cassandra deployment we did. So the first one was pretty much a mess. And the basic reason it was pretty much a mess is that we took an existing relational database schema, we were storing data in Postgres, and we just said, okay, let's do the exact same thing in Cassandra, and that is a bad idea. And having a bit of understanding of what's actually going on at the lower level and how Cassandra is representing this data internally and on disk will allow you to very effectively reason about the types of structures that are going to allow you to efficiently interact with your data. So the basic structure of our low-level Cassandra data is called a column family. And it looks a lot like a Ruby hash, or like a hash in general, a key value structure, where the values themselves are also hashes. And these inner hashes also have the property that they maintain order by their key. So you can see that here. That is not a coincidence of insertion order or anything like that, or just how I decided to display it. These inner hashes will always be in order. So let's look at this in a more traditional way of representing a column family in Cassandra. So we've got, on our left, we've got a row key. And then we've got several columns. And the columns contain a column name and a column value. And you'll notice that I didn't line up the twos there. And column is actually a pretty terrible name for what's going on here, because there's no fixed set of columns that this structure represents. So we can have 1, 2, 4 in the first one and 2, 7 in the second one, and every row can have completely different column names, and that's fine. It is really more like this hash, where it's just a bunch of key value structures inside each row. Now we call these wide rows, and the reason we call them wide rows is that you can put about 2 billion columns in every row at this level. And that's about where the people who maintain Cassandra would recommend you stop. But 2 billion is a lot. I'm guessing most of you don't have 2 billion columns in any of your relational database schemas, but I would be impressed if you did. So the most important thing to know about wide rows is that each individual wide row sticks together. So that means that when a wide row is stored on disk, each individual row lives in a contiguous part of disk, and in fact, the data within that row is on disk in sort order. So if I want to read a single row or a slice of a single row in a range of column headers, I can do that very efficiently. That's one chunk of disk. I just have to find one thing. And sort of as a corollary to that, the wide row, a given wide row is going to live on the same set of machines. So if you're replicating 3 times, any given wide row is going to be on 3 machines altogether. So bear that in mind as we keep looking at our schema. One small note is that under the hood, Cassandra has a concept of compound types. These are just tuples. Cassandra has a pretty normal type system, pretty much anything that you would expect from any other data store. But you can also have a compound type, and those have a defined order, which is just like sorting an array in Ruby. Basically, sort by the first thing, and then if there are duplicates in the first thing, sort by the second thing. You can keep going with that. So let's take a brief step back up to the CQL table we created and the way we're actually dealing with our data. So here are a few values for our blog. I've got a blog about my cat, and I've got a blog about code. And so, that first column, the subdomain, is going to separate out the blogs. And let's look at 4 roles that exist within the data here. So we've got the partition key. We talked about that. So everything for a given blog has the same partition key. We've got our clustering column, which defines the order. Now, I put dates in here, and you'll keep seeing dates because UUIDs are really, really long on a screen and just jumbled. But think of these as UUIDs that represent the given dates. Then we've got names of our data columns, so title and body, data column names, and we've got the values of our data columns. And that's just the values that we would think. So take this in while I take a deep breath, and then we are going to look at how this is actually represented under the hood. Okay. So here's what it looks like. We're basically taking, for every blog, we take all of these skinny rows, and we're going to project them into a single wide row. And the headers of the columns in our wide row are compound of the clustering column and the name of the actual data column that we think about as the column name. So what we're going to have is we're going to have all of the rows for the blog, and they're going to be in sorted order, just kind of all next to each other. And within each row, like you've still got the columns all broken out. But they're all sticking together in a wide row. So what are the consequences of this? Well, it means that if I want to do something like that, that's going to be really efficient. All I'm doing is I'm saying, give me the end of the wide row that's at the mycat partition key. And so all I have to do if I'm Cassandra is go find it on the disk and read that range off the disk and bring it back to you. And it's already in order, and everything is going to work just as we want. And that is, in fact, why we chose this particular schema. So like I said, the schema you choose is what is driven by the way you're going to access your data. So this is the basic thing I want to do on a blog, is I want to access the most recent 10 posts. Another thing we can do very efficiently, and this happens to be another good use case for a blog data model, is ranges of our clustering columns. So in this case, we're going to look for everything in September from the mycat blog. And as I'm sure all of you are imagining in your head, okay, well, that's look for the beginning and the end of that range within the wide row and give it back to me, and it's going to be super, super efficient. So using secondary indexes, like I said, should not drive your core data access. And the reason for that is that if I'm just getting a bunch of posts, they're going to be living in random places, in random wide rows, potentially, under the hood. And so, yes, the secondary index does efficiently let me figure out what rows I want, but when I actually go to get them, that's going to put a fair amount of strain on the database to find it. So this is legitimate, you can do it, but if it's the main big operation you're doing all the time that has to be super performant, you probably need to choose a different schema. Or you might denormalize. So we have a fair amount of scope to not denormalize here, but in the end, you probably will end up either kind of building a table that acts as a secondary index, or you might just build a table that denormalizes certain things in a particular order or range of things that you want to get them in, and sort of hand roll it that way. Another way we can really use our Cassandra database most efficiently is to, if we are doing a lot of writes, to try to do that without reading. So here's an example of adding something to a set. I have no idea what's in the set right now. I just want to add something to it if it's not already there. And I also want to update the title. And because Cassandra's write optimized, this sort of pattern, particularly for high volume writes, will work really well in keeping Cassandra happy and efficient and performing well for you. But as soon as you start trying to read and write, you're going to find that things are a little more sluggish to deal with. Now, of course, it's fine to be reading from the read parts of your application. So some of you may be wondering, what about the blogs table? That does not have a compound primary key. It does not have a clustering column at all. So the wide rows in the blogs table are not wide. And because of that, there is no defined sort ordering. It is in an order, but it is not a meaningful order. So we can't do anything fun like ordering by subdomain. Similarly, we can't do range type queries, like a greater than or less than or between. Also not an option. So really, these top level models, the ones that have a simple primary key, should really be a single entry point into the data they own. So in this case, for the most part, we're only ever going to be dealing with one blog at a time. So it's perfectly reasonable to load a single row out of a simple primary key table. And we can do a bulk load and say, give me these 100 keys, and that's also fine. But manipulating them in any sort of meaningful way with respect to a collection of them is kind of out of the question. So I do have some tools for you to work with if you would like. If this sounds appealing and you would like to just scale your data out like crazy and never have to wake up in the middle of the night because the database is down. So this is a library called Keycool. It's been around for a while. However, just this morning, I released the pre-release of the 1.0 version, which it lets you do all of the things I showed you. So actually, a lot of the stuff in CQL that has been in this presentation is pretty new. It's the third version of the CQL language. So you get an active record-like domain model. You represent the relationships between sort of parent and child in an active record-like way, and that translates into a compound primary key. So we can take a look at what that looks like. Blog, single primary key, and then post actually says, well, I belong to blog, so my partition key is going to be the blog subdomain. And then it has its own ID. You can deal with collections quite easily, so they just act like the Ruby version of that collection, and we, under the hood, will persist changes to those collections in the way that you did it in memory. So if you push something onto a list, we're going to push something onto that list in the save statement. For the most part, it works just like active record, so it's quite easy to use, but my goal with designing Keycool was to make sure that doing things the right way, doing things the way that we've talked about today, is easy and natural, and the thing that you want to do when you look at the interface, and doing things the wrong way is awkward and doesn't feel right. In hopes that you will not only become a dedicated Cassandra lover like myself, but that you will be able to get there with a minimum of pain. So that's all I've got. I hope some of you will go check out Cassandra and use it for your big data needs. And I'm sure everyone's hungry, so please feel free to hit me up at lunch or on the internet. There's a link to Keycool itself and my email. Hit me up. Thank you.